All right. Suppose the sequence an diverges to positive infinity and the sequence bn converges to b, which is negative. Prove that the sequence an times b of n diverges to negative infinity. Okay, we're going to start by using this piece and get an upper bound on this one, and then get an upper bound on this one, and then we'll use that upper bound to show that an bn is less than or equal to some sort of real number. Okay, so we're going to start with this piece. So I'm going to assume bn converges to a b, which is negative. I'm going to let epsilon be positive, and I will choose the epsilon to be the absolute value of b over 2, kind of like we've done in the past to get bn to be bounded, because we want an upper bound on bn. Okay, now we'll use the definition of convergence. So there exists n1, I'll use the n2 for the other sequence, such that for all n greater than or equal to n1, we have that bn minus b is less than, we chose epsilon to be absolute value of b over 2. And I'm just going to use the inequality and absolute value property immediately to say that implies negative absolute value b over 2 is less than, sorry, no absolute value anymore, bn minus b strictly less than absolute value b over 2. Okay, and we're going to note that since b is negative, the absolute value of b is equal to negative b, because it takes the negative number, turns it positive, so this is a negative number, but if we multiply it by -1, it just turns it positive, does the same thing. So these are equal, and we can use this because we can add b to everything, and that would give us a negative b, so we'd have b over 2, plus b is 3b over 2, and then over here we'd get negative b over 2 plus b, which would be just b over 2. So we get 3b over 2 is less than bn is less than, this is our bound that we really want, it's just b over 2, since it was negative b over 2 plus b over 2. And we have an upper bound now for bn. We want to get our upper bound for an. So we want to let k be some negative real number. And we're going to use the definition of converging to positive infinity to say that there exists an n2 such that for all n greater than or equal to n2, an is greater than or equal to, I'm going to say k, and then we're going to divide that by b over 2, this bound, because we want the bounds to get rid of each other. B over 2. Okay. And now we want both of these bounds to work. So one works with n2 and one works with n1. So I'm going to take the maximum of the n's. Let n equal the maximum of n1 and n2 to ensure that both properties work, because we want to use both properties. And for n greater than or equal to n, well, now we consider what we want. an bn is less than or equal to, well, from the first inequality, we know that bn is strictly less than b over 2, so I can replace that with b over 2. And b over 2, remember b is negative, so this is a negative number times, this is also a negative number, because k is negative and b is negative. Negative over negative is positive, and we're multiplying this by this negative number. And so this ensures that this inequality will flip and it goes in the right direction. And so we have that k over b over 2 times b over 2 is equal to k, which is the exact definition for diverging to negative infinity. Thus, the sequence an bn diverges to negative infinity. And the proof is complete.